invited him here today to talk to you. And that's the story. So, take it away.
Yeah, so you guys got my poster, you got the abstract. What do I want to talk about? Well, I'm just going to give a little bit of a, let's take a motivation for the talk first, and then we'll get to business. We all have taken Math 230 here. Or if not taken Math 230 here, we've taken some sort of multivariable calculus class. Now, that multivariable calculus class is, it's a big improvement upon the calc class, or the two calc classes you've taken before, which were just functions on the real line. Now these functions are on three-dimensional space that we did in the calc class. And there's a lot of things that we, I guess, the teacher or professor proved for you in that class. But a lot of those things kind of only work in R3 Euclidean space. You can extend a lot of interesting things that calculus can give you to more interesting spaces. So I'm going to have a good number of examples of spaces. For example, there's the punctured plane, which is just R2, or the two-dimensional Euclidean space, but with a point removed. There's also the punctured Euclidean R3, which is the same thing, R3, but with one of the points removed. I also have these guys, which represent S2, a sphere, and T2, a torus. Now these are all four of those that I gave are examples of spaces in which you can do calculus. Right? You can do multivariable calculus in all these spaces, but things are different. Now what exactly is different is not like the more basic stuff or the some of the direct computational stuff, or I guess the best way to say it is like the local stuff. The stuff that's different is not like, oh, if I have a function here at a point, like can I take an integral around a quick? Most of those rules are the same. The differences in these spaces are all, in some sense, they're global. In some sense, if you zoom in on a close patch, you don't see the differences. The differences you only see is if you zoom out and you see the whole space. Now, I say global, but what you should be hearing is topological. Now, these spaces are different topologically. Now, what does that mean? I'll explain that to you. But first, I want to give an example. I want to give an example. This actually isn't an example, but I'll write this down. Let's say I have a vector field, F, it takes a point in R3 and gives you back another point, which is the direction and magnitude of the vector. And this vector field is such that the curl of this vector field equals 0. Now, there is something that we know about vector fields and curls. We know that if f is some gradient, or is the gradient of some other function f, so this is a vector field, and this is just a function, if this is the scale, then this is definitely true. This is going to equal this, and you may have or may not have done this computation, but this is just going to be 0. You're going to have things canceling out, and this is always true. But the other question can be asked. The question can be asked is, now question, let's say this, if f has 0 curl, is it equal, or let me write it in a better way. If the curl of f, this big F, vanishes, does that imply that f is the gradient of some function. What do you guys think? Let's take a vote on this. Let's take a vote. How many for yes? Just raise your hand. One, is that a yes? That's a yes. That's one for yes. And how many for no? 1, 2, 3, 4, 5, 6, 7. So we have a yes and a no. And the answer is, as always, it depends. Now, what does it depend on? Like you may have guessed, it depends on the topology of my space. Now, in R3, in R3, it is true. And there's actually a formula for this. So, let's say that my function curl of f equals 0. Then, you can actually define a, where did I define this? Then f of x equals integral from 0 to 1 of f tx dot x bt. And now, this is just a computation. If you take the curl, or if you take the gradient of this, you will end up with this. Now, there is an important assumption that is made in this formula and in the calculation of the formula. That assumption is what we call, you're in a star-shaped region. So what that means is, I'm in a region, let's say, such that if I have a point, every single other point can be met with this point through a straight line. And you can see why you need that assumption, because I'm integrating from 0 to 1. I need this guy to be able to go from 0, f0, to 1, which is going to be f of x. And right, x is the point which we're at. So if this is like the origin, the 0 point, and I want f here, I need to be able to draw a straight line from here to here. Now, star-shaped regions, by definition also, some star-shaped regions have what we call trivial topology. But we can actually still construct certain vector fields such that this does not happen, or such that it breaks the rule. And we'll see that the rule breaking happens in a way that means that your space cannot be Arthur. And I'll explain that for you in a second. So we have this as a result. This is one example of the more general Poincare theorem, or Poincare. Now, let's consider a vector field f, which equals, should I get signs right? Negative y over x squared plus y squared, x over x squared plus y squared, and 0. So if you want to picture it, it's just, around the z equals 0 axis, it's going in a circle. and as you get closer and closer to z equals 0, or to the z-axis, to x and y both equaling 0, it's growing larger and larger in magnitude. So if I choose to like look down from onto the xy plane, because the z-axis is 0, so I can just draw it like this, where I have a point here and a vector field like and it's growing smaller as it's going on to infinity. But it's good, so like here it'll be like here it'll be here, and it's going in a circle. But it'll be a bit bigger, I guess. It's not the greatest drawing. And then this, you can think about it like it's like stacked up. So now you can ask what happens at the 0 point. Well, before I do that, that's actually kind of spoilers. But we can compute the curl of this. The curl of f is 0. 0. But there is no f, so what does not exist, f such that gradient of f equals 0. So why is this the case? Well, this is the case for the same reason why I skipped over what's happening in the origin. What's happening in the origin? Can somebody just shout it out?
Undefined.
It's undefined, exactly.
Singularity.
Singularity is another way of saying it. But yeah, not only does it blow up, even if it doesn't blow up, even if I, just made it negative y and x, here, it's no longer continuous. That's the more important thing. Because we want to talk about vector fields that are continuous and also differentiable, because we want to be able to take derivatives of them. So these are not continuous or differentiable. And here, it's worse, it blows up to infinity. So what can we do about this? What we can do is we can just remove it. We can just remove that point. Or in this case, the axis. So now, if I take my space to be R3, but I remove, let's say x equals y equals 0, what I've done here is I've removed the z-axis, and now I have allowed this vector field to exist, because now this vector field is perfectly fine. This vector field is perfectly fine in this space, while it was not fine in R3. Yeah?
Okay, this is kind of an amateur question, but I thought the curl gave like an axis about which it rotates, right? Is that, or am I thinking of something else? Like, isn't there kind of, when you take the curl with the field, it gives like the axis about which it would spin or rotate?
Yeah.
So since it's rotating about the z-axis, why would the curl be 0?
Yeah. So the one thing is, the first thing is that you cannot take the curl at the z-axis because it's not defined. It's vector blows up, and every other point the curl is 0.
Oh, I see.
Like if I look here, because like actually I've chosen these coefficients specifically. When I say coefficients, I mean like powers, like x squared plus y squared, which is r squared. R squared here is chosen specifically to make the curl vanish, because if I look at a point here, right, it's slowing down, or it's the field going this way is losing magnitude in just the correct speed to make the seeming curl of it disappear.
I see.
So the curl at any point like this, or in any neighborhood, ends up being 0.
Okay. Thanks.
So this vector field is fine in this space. Now, what is special about this space, topologically, if I don't want to talk about vector fields, if I want to just say, okay, I have R3, but this guy is removed. Now, the things to think about are, let's say these two circles. This one goes behind, and this one goes in. So one circle encloses the this removal, and the other circle doesn't. Now, one property that is very, I would say, important is the fact that this circle can actually be continuously shrunk to a point, while this cannot. You try to shrink it, you know, you can't go through this axis because this axis is not allowed. You have removed this point from my space. Well, here it can be. Now, if I was in regular R3, if I remove this, I'm able to do that. I'm able to shrink this to a point. But with that line, I'm not able to. Now, there's another thing that you can do with vector fields that also has to do with curls and divergences. It's integration. You can integrate them. Now, another example essentially of what's going on here using Stokes' theorem is that if the curl is 0, that means that the integral over any surface of the curl of f should also be 0, right? But through Stokes' theorem, we know what this is. Well, this is just going to be the closed integral of the boundary of A. This is f dot d gamma. All right, so whatever. Actually, no, yeah. So gamma is a closed curve. That's just the boundary of A. And f dot this, that just means I have let's say the vector field. I should say this and dt. Let's write it that way. Right. And again, if we're in R3, the curl of f is 0 implies that f equals the gradient of some function, little f. This, and as we know, this is just 0. Now, if I want to compute integrals of this specific vector field, we can actually compute two integrals. And because I don't want to write it all out, there's going to be a little bit of trust me bro going on. I have two types of circles I can do it on. I can do it around this loop and not around this loop. If I'm not around the loop, the integral is going to be 0. But if I do go around the loop, specifically, I can write down the easy case. If gamma, let's say gamma of t equals, how do I write it? R cosine of t, or sine of t, yeah. Let's say 0, doesn't matter where we are on the z-axis. You know, this loop around this f And in fact, and this is an exercise to the audience, if I have any loop that can be continuously deformed from this loop, so any loop that goes around the z-axis once, with going this way, the integral is going to be 2 pi. And now this is kind of, I think, an intuitive example of what's going on, topologically, and how topologically can sometimes mean global. Now, what I have just told you, not proven, but told you, is that if I have any loop that goes around the z-axis, any loop, so loop could, your R could be like 50,000. As long as it goes around the z-axis, the integral is going to be 2 pi. And if it doesn't go around the z-axis, it's going to be 0. So, what is the difference between this loop and this loop? Well, one thing I mentioned was that these can be contracted, but there's another more important property that I should mention, and that actually relates to what's going on here, which is that this loop encloses a surface. This loop is the boundary of a surface. And I can draw that surface. I could draw any surface, but I'll just draw the most obvious one, just the sphere inside of it. But these loops do not. See, this loop, if I try to make a surface inside of it, I'm always going to go up against this thing. I'm always going to go up against this, what I call deformation. So it's the loops, it's the closed loops that are the boundaries of a surface that give you an integral of 0 with this special vector field. And it's the closed loops that are not able to be the boundary of some two-dimensional surface that give you integrals that are 2 pi specifically. You can also mention winding numbers. So if I go around twice, it'll be 4 pi obviously. If I go around 3 times, it'll be 6 pi. And if I go the other way around, it'll be negative 2 pi. And yeah. So the question is, what do these vector fields and these loops have in common? And there is a common structure that they have. The structure is a topological structure. It has to do something intrinsically with this space that they live in. And so I'll just write something down, which is, if I take all the possible vector fields, so give me the vector fields. If I take the vector fields that have 0 curl, but are not equal to some gradient of f, these actually form a space. There's a type of space that they form. And it's actually a vector space. So we have special names for these things. So Z, I'm going to say, Z is going to equal the vector fields such that the curl of f equals 0, and B is going to equal vector fields such that they're equal to some gradient. And the group I care about actually is neither of these, is this, H, which is going to be Z my V. These are the closed ones, these are the exact ones, what we call them. Closed and exact. Now this is a vector space. It forms, it's what we call a homology group. And so the group structure is what we care about most. And this is one of the elements in this group, but there's a lot of elements in this group. And there are specific ways of combining them and what's the word I'm looking for? Composing them and whatnot. But there are other groups I can form. Say Z for vector fields. Now, I also have things like this that I can do for these loops. So Z, let's say for loops, equals loops that are closed. So just closed loops, that's simple. And B of L is loops that are boundaries. And as you may guess, H equals ZL over BL. Now the drawing is a bit easier to do here. You don't have to draw a whole vector field. But just to give the same example, so I'll draw a couple loops. Let's draw this one, let's draw this one. Now let's draw this one attached to this one. In this group, these two are actually the same element. These two are the same element because this is one loop. Like I'm saying I go around here once and then I go around here like this. These two are the same elements though because this loop is actually the boundary of another of some surface, which is this surface. And so you can actually continuously deform it to be this loop. The important part are these continuous deformations that I'm talking about. These are called homotopies. You may learn that, I don't know how many of you have taken topology or are in topology right now, but these are important. And these are both homotopy invariants. So what that means is if I have a continuous map between things, then I can, for both this guy with these loops and this guy with the vector fields, I can you create a equivalence class basically. So you're able to say that two things are the same basically. And in fact, for these groups, for this space specifically, my thing is this. And thing is this. It's a bit easier to see with the loops. You actually create a group, which is this. And the way the group works is, if I go around once like this, that's one element. But if I go around twice, that's two. If I go around three, that's three. And if I go around backwards, that's -1. And if you go around like once, and there's a way to compose loops as well, right? You literally just like do one and then you do the other immediately, or something that's homotopic to the other one. And this is the group you get. And there's a similar thing with the vector field, just the picture is a bit more difficult. And so the more easy way to say is you have vector fields that are the curl modulo these guys. So if I have one vector field, let's say I have one vector field f, or let's get another example, A, is going to equal A prime if A prime equals A plus some gradients of f. So if I have a vector field and I add another vector field that happens to be the gradient of another vector field, because I'm modding all the gradients out, these are the same elements. Now, there's kind of maybe like an obvious punchline because of the way that I've set this up. But what do these two groups, this HL and this HV, have to do with each other? Well, they're isomorphic. And they're isomorphic not just for this space that I've drawn, but for any space. For any topological space, they're isomorphic. So another example, and this is just another example. Another example is the torus. This guy. I won't draw it on here right now, but I want to draw the torus like this. You've all, I'm assuming, have seen this way of drawing a torus. All I'm doing is I'm taking a part of the Euclidean plane and I'm like connecting this to make a cylinder and then connecting the ends to make the torus. And I don't actually have exact expressions for this, but I have a picture, which is the best I can do. So let's say this is my vector field, and part of my drawing, but this is continuous, or this is a constant vector field, right? So you can imagine it would go around the torus and just wrap up against itself like this. Now, this vector field has a curl of 0, which is kind of obvious if it's constant, so all the derivatives can be 0. But if I take an integral, let's say I take a loop like this. So in the picture here, it would go like this. And if I take this integral, that's going to be some number. But if I take this integral, that number is going to be 0. So this number is just, it's just going to be like the length of this loop times the magnitude of this vector field, right? Because it's an easy one. But I wanted to point this out because topology is not just taking R3 and making defects on it. I gave that example earlier because it's a simple example, it's an easy example. But you can think of this guy, and now you can ask, let's figure out what HL is. Let's figure out what this is. And because it's pretty easy to just picture, I can do that. So if I think about the loops that you have here, any loop just like this, well, that can always be contracted. Or another, a better way of saying this is the boundary of some space that's inside here. But if I take this loop, there's no space for which this is the boundary. You know, if I try to even like draw a boundary or something, it just ends up wrapping around itself and it becomes the entire space. That doesn't make any sense. Right? I can go around twice as well, or I can go around backwards. So we have another similar thing, which we had before. We have a Z. But there's another loop. The other loop is this guy. And the same exact thing happens. The same exact thing happens, you can wrap around many times forwards backwards, and you find that the homotopy group, or not homotopy, what we call the homology group, is Z2, or Z cross Z. So we have one Z coming from here and one Z coming from here, and all other loops that are not homotopy equivalent, or any other loop that does not go around here or here, is just, is the boundary of some surface. So again, this is just an example, but what I did here, this is calculus on a torus. And the rules of calculus are all the same. The rules of calculus are all the same, right? Like I do the integrals all the same way, I define vector fields the same exact way. But the answers that you get globally are different. There's another quick one I did want to do. You can ask, okay, you mentioned these types of defects. There's another defect that I can just quickly give an example of. This is, but let's say R3 without the point. And the story is very similar. And even before I do that one, the story is very similar when you have curling gradient. Now we know that if, let's say f equals the curl of some other f, then the divergence of f is going to be 0. Is it true the other way around? Can anyone guess the answer?
No.
Close.
Maybe.
It depends. The answer is it depends. Now what does it depend on here? It's a very similar construct, but again, what I'm going to do is I'm just going to say, okay, R3 without this guy. And this time my vector field I'm going to choose. My example vector field is going to be, what's it going to be? Let me check what's going to be. X over, I'm going to use X and R cubed, Y over R cubed, Z over R cubed. And R is just square root of X squared plus Y squared plus Z squared. Now, here's the view. The divergence of F is 0, but F is not the curl of any vector. And the picture is still pretty simple. I have a thing here, and and it's just going upwards, except in like 3 dimensions as well. It's a pretty simple picture. And now you may be asking, you can ask a similar question that you asked before, which is, oh, isn't the divergence supposed to be telling us how things are going away, right? How points act as a source for vector fields? Well, because the vector field is like shrinking at the right rate, it actually does not seem it that way at any point here. And this point's not allowed. So I can do a similar thing, except I don't integrate over a circle. What I'm going to be doing is I'm going to be integrating over a 2-sphere. My surface is just going to be defined by x squared plus y squared plus z squared equals some capital R squared. So like integrate. And this is just a number, which I'm actually just going to choose to be 1. And the integral turns out to be over S. This closed thing turns, what was it saying? Yeah, F dot ds. That's going to be 4 pi instead. Now, you already kind of know the answer to this because I did the same exact thing earlier, but can you predict what the integral of a two-sphere that does not contain this point is? Like, so maybe a two-sphere that's right over here. Can anyone predict what the integral of this flux is going to be?
B0?
It'll just be 0. And through the similar argument here, right? If the divergence of f is 0, then the triple integral over a volume is going to be 0. But we know that a triple integral over a divergence, or yeah, we know through Stokes' theorem that the triple integral over a divergence is just the flux through the surface. And that's going to be 0 as well. And so any surface that doesn't contain this is going to be 0. And the same thing that I told you was true for the loops around the defect is true for any two-sphere enclosing a point. Which is that if I have two spheres, one here but another one like deformed here, or one like 5 times as larger, the integral of the flux over the two-sphere is going to be the same. It's going to be 4 pi. This is another homotopy invariant. So now, I'm kind of doing the same thing, but with different things, right? In this case, ZV is going to be F such that the divergence of F equals 0. VV is going to be F such that F equals the curl of some other vector field. And H is going to equal ZV over VV. And the same thing here. Let's say ZS is going to equal two spheres such that, or if closed S2s, BS is going to equal S2, which are, or let's say this, which equal the boundary of some volume V. And by that I mean, it's enclosed some space. And this space, H of S, is going to equal ZS mod BS. Now, can anybody guess the relationship between this space and this space? They're isomorphic. They are isomorphic, yes. So another example is like the sphere. Now I can't draw circles on the sphere. I can't draw circles here. Because if I draw any circle, it's always contractible. I can always bring it down. Or, more importantly for us, it is always the boundary of some space. This is the boundary of this guy, but it's also the boundary of the one that goes around it. But either way, it's the boundary. And boundaries, as we know, you mod over. But, so the ZLs are completely trivial. Right? The ZL here, oh, whatever. or the HL is completely trivial. But if HL and HV for any space is trivial, or isomorphic, what does it say about HV for the sphere? The set of vector fields such that the curl is 0, but mod it out with the space of vector fields such that they're the gradient of some other function. Well, that group has to equal this group, right? And for the sphere, this group is trivial. You can say 0. So that's also 0. So this group being 0 or trivial, what does that mean? Well, group theoretically, if this group divided by this group is trivial, normally, maybe there's some subtle details there, but we would say that they're kind of equal to each other. They're actually isomorphic. Yeah. So that means that every single vector field whose curl is 0 on this two-sphere is the gradient of some constant function. But that is not the case when we get to the next ones. So we say a higher homology, because you can have vector fields who have a vanishing gradient, but who are not the curl of some function, of some other vector function. And this group is also non-trivial, because you have a two-sphere here that is closed, but is not the boundary of some other volume, which, the first example is just this guy. Because remember, you only have this guy as a surface. So this two-sphere is not the boundary of some, you cannot consider this the boundary of some other space. Because the inside of it, that's not part of the space at all. Doesn't count. So this guy, again, is Z. It's a bit more complicated here because you can have mappings which overlap spheres and whatnot. It's a bit easier if I just go around in a circle twice, but you can do the same thing to spheres. And because of their isomorphism, you can Z as well. So I'm running out of time now, but this is a generic theorem, which we call de Rhams isomorphism, which says, I'm going to be a bit more generic, which says that for a manifold M, the H, and I'll say what these mean, P of M is isomorphic to H P of M, let's say coefficient Z, maybe, or R, that doesn't matter, or one of these should count. So what's going on here is that I'm saying I have a generic space M, and I have, here I use vector fields, but if you know anything about differential forms are the ones that you care about when you go up to manifolds of higher dimension. The properties, or this isomorphism is saying the same thing as these two isomorphisms, but it's kind of compacting that information on board. What I'm saying here is, if I have a loop, or some closed S, S to the n, and I take all the closed S to the n's and I mod out the S to the n's, the n spheres that are boundaries of some space inside that are some boundary. I take the question that's going to be space, and that space is equivalent to the n forms that are closed, or whose exterior derivative is 0. And this is just a generalization of both the curl and the divergence, or the gradient. In this space, modding out the ones that are curls and divergences. Sorry, I kind of said a lot of terminology in that last bit. But my point is that the topology of a space determines two things equivalently. It determines the types of loops and the types of spheres I can make. And it also determines the types of vector fields I'm allowed to make. Because again, this vector field would not be allowed in R3, but it is allowed in R3 puncture, in the puncture R3. In the same way, NS2, that is not the boundary of some volume inside, is not allowed in R3, but it is allowed if you puncture R3. And these things are not just, random or, I would say this is significant. These are global properties of the space. So I can measure stuff like this very, far out if I want. And I mean, one example where this idea has a lot of uses in physics. If you ever heard of the Aharonov-Bohm effect, that's actually exactly what this example is, where if I go around a magnetic monopole, I'm going to pick up a phase. But if I go around something that's not a magnetic monopole, I won't pick up a phase. The integral here is 0, and the integral here is 2 pi. Okay, I think we started late, so. Yeah, I'll end out here. But do any of you guys have any questions or anything to clarify? I didn't take any pauses during that talk. That's my bad. But okay, yeah.
So when you say like enclosed by a volume, I know that doesn't really make sense if you don't, like, do you need to embed it in like a Whitney embedding into a higher space to then say that you can like kind of make a volume inside that higher space or surface inside that higher space for that curve?
Which one are you talking about specifically? What are you talking about? Can you be a bit more specific?
Like when you describe, like when you have a loop, it's the boundary of some surface. Is that after embedding your manifold in a higher space that you're?
No, well, the ones I was talking about was just R3.
Okay.
And so in R3, if you have a loop, you don't need to embed it. Because, the point is to not embed it.
Okay.
The point is we're talking about intrinsically about the manifold itself. And so I'm able to have a space. Like, for example, here,
Yep.
I'm able to say that these have a boundary, or these are the boundary of some, some area inside, but I don't need a Whitney embedding of this,
Just saying it's like the boundary of a submanifold. Is that kind of what
Yeah, sure. I mean, like, this is the boundary of a submanifold
Okay.
in R3.
Sure.
Any other questions? Anything that's confusing about the setup?
How long would it take you to drive that formula up there?
Which one, this one?
Yeah.
If you know, it's a trick, kind of, but if you know how to do it, it doesn't take very long. Like, if you know the trick, it doesn't take very long, but coming up with the trick might take a while, I don't know. But like, if you asked me to just like derive it and you told me the trick, it would take me maybe like not even 10 minutes. It's not difficult proof.
That equation holds for any path.
Which equation?
So for that f of x, that when you're solving for the scalar, the vector potential, does that work for any path provided it's convex and not just star convex? So you can take a path from the point to one you're looking for.
No,
Okay.
it doesn't. Because if it did, it would work for this space.
Mm-hmm.
Right? Because if I'm here or whatever, and well, I guess this is 0, but this being at 0 is not super important. If I shifted it to non-zero and then I had a point here and here.
but the fact that line's there would make any set that contains a not convex. Well, sorry, it would be convex, never mind, not sorry, like, okay, I see what you mean.
Yeah.
I thought-
You want the straight line.
Okay.
You want the straight line because then this, like, you can do it by hand. If you take the divergence of this guy, you're gonna get this guy. If it wasn't star convex, then maybe you wouldn't. I mean, maybe you can say something like,
It's like unique.
you need some continuous thing, because if I am here and here, like, there's no continuous way of going all the way around, if you see what I'm saying. Like, if I have something like this, right? I have a continuous way of going from here and maybe like this. Maybe there's more complicated formula there, but if I have a puncture, I don't really have something continuous anymore, because, like, what do I do here? And then I have to jump over here. And maybe you can say that these lines have to be all, you know, you have to be able to go around.
That means it's simply connected.
Something like that. Yeah, and that could be up to the connectedness of the space.
It's just like.
But the simplest formula, you want a straight line, because then you don't have to do more complicated with this. Okay, I'm over a bit, but thank you all for coming.